Okay, we've got a number of interesting things to talk about today. Hopefully I don't have any technical difficulties like I did this morning. I've updated this tool and hopefully that will resolve a lot of the issues we were having. Um, if you if you didn't tune in to my homework solutions uh, lecture, I suggest that you do so. Everyone who submitted homework missed a few problems here and there, and so nobody did the homework perfectly. And so I actually go through the homework solutions in depth, and I've uploaded that recording to the Learn system. Okay, that was a painful recording because of all the technical difficulties I had. So I put a lot of effort into that, so you should go check it out. So today what we're going to do is we're going to finish up chapter 4, and with any luck we'll get into chapter 5. And I'm also going to spend a little bit of time talking about um, a couple of different other architectures, another MIPS architecture, and the Intel 486, as well as a quick glimpse at the Pentium architecture. To give you an idea of where, where the commercial world has been and is going right now. So, and we'll talk. Part of what I have prepared here for the end of chapter 4 is talking about beyond pipelining. Now, of course, when you take my 538 class, we will spend most of the semester talking about the beyond pipelining part. But for this class, we just kind of brush over it fairly quickly. Okay, so where we left off last time is talking about exceptions. So exceptions are a means for our processor to handle unexpected internal or external events. Okay, internal exceptions can include address error on fetch. In the fetch stage, we could have a decode error, also known as an undefined instruction or reserved instruction error. Okay, in the decode stage, in the execute stage, we could have an arithmetic overflow, and in the memory stage, we could have an address error on on read or write, and we could also have a bus error if we're interacting with a peripheral. Okay, and there's a whole bunch of other types of exceptions that we could have, a bunch of them centered around virtual memory and everything, which is more advanced topics that we'll come back to when we cover virtual memory in chapter 5. But as we mentioned, there's a little bit of complexity that comes along with pipelining and handling exceptions. Specifically, we want exceptions to be precise. Precise exceptions are absolute must for actually recovering and from an exception and picking back up where we left off. Okay, sometimes exceptions are unrecoverable, and when a particular exception happens, the only thing the system can do is halt. Um, and of course, you've encountered similar exceptions in your programs that like a virtual memory fault with your program is what Windows likes to call a seg fault, segmentation fault. But in that case, the operating system is still operating, but your program encountered an exception that the operating system didn't know how to fix. Um, and it's up to the system designer how to handle these various exceptions. But from the hardware perspective, we have to provide a mechanism for gracefully recovering from the exceptions. So if you recall, what we do in our pipelined architecture is we well, for MIPS, we stop executing um, the offending instruction, and we store the PC of the offending instruction in the EPC, and then we store a cause code in the cause register, which will then allow us to our exception handler to then determine what caused the exception. Okay, and the EPC allows it to know where to return to. It also points to which instruction caused the exception. Because sometimes if it's like an arithmetic overflow or something like that, um, there may be some things that have to be done to correct that. An undefined exception actually can happen quite often. Sometimes you may choose to emulate particular instructions in software rather than implementing them in hardware. And so what will happen is when the processor encounters an instruction that its hardware doesn't support, it throws a reserved instruction exception. The exception handler will then go and look at the cause code and see, oh, that's a reserved instruction. So then it'll use the EPC to go figure out what um, that instruction was. It'll go pull it up. And then in software, it can actually decode and execute that instruction. Okay, and so that's software emulation of instructions. Okay, and that's done quite a bit as well. So okay, so that's how MIPS handles exceptions, and specifically the way we're going to handle them in our pipeline is we're going to detect the exceptions as they happen throughout the pipeline, and then we'll flow exception bits down the pipeline with that instruction. And then when we get to the end of the instruction execution, which the book shows an example of it in the handling exceptions in the execute stage. You could handle them in the mem stage, or you could wait all the way to the write back. Okay, and so there's advantages and disadvantages of each of these. For our processor, we handle exceptions in the memory stage, and so when an instruction gets to the memory stage, we determine whether it has detected an exception along the way, and if it has, there's also a priority of the exceptions, and the instruction set architecture defines that priority. Um, and so, for example, an address exception on fetch is of a higher priority than a reserved instruction, right? So, um, so, so anyway, then the hardware will figure out which is the highest priority exception, and then that's what um, it uses that exception to set the or it sets the cause register with the cause code of that highest priority exception. Okay. So again, what we're doing is that's how we handle it in pipelining, because pipelining is a little complicated in the fact that we're overlapping instruction execution, and so we basically detect the exceptions as they happen in the pipeline, keep track of them, and then at the end of the instruction processing, we then handle the exception. And again, we handle it by storing the EPC, storing the cause code, and then redirecting the program counter to the exception vector. And as I mentioned before, that depending on the exception, it may vector to a different location. Okay, reset has its own location in MIPS. It's different from, for example, a TLB exception, which we'll talk about when we get to virtual memory, and that's also different than the way general registers or general exceptions are vectored to. And then, of course, vectored interrupts take it a step further, where every interrupt has its own address to vector to. Okay, so we want to maintain precise exceptions, and so again, we do that by handling all the exceptions at the end, and we don't allow an instruction that the offending instruction and any instruction that follows that offending instruction in program order to commit state. Okay, and that means that we haven't done anything that we can't undo. Is another way of looking at it. Okay. Okay. So um, when we move to more advanced architectures, so deeper pipelines and floating point support, or we start running instructions out of order and whatnot, maintaining precise exceptions becomes more difficult. And in a little while, I'm going to talk about just real briefly out of order execution, and I'll point out how with a reorder buffer we can actually maintain precise exceptions. Okay. All right. Well, let's do something fun, and let's look at the 486. Okay. So I don't know if any of you remember when the 486 came out. You probably were very small at the time, if not, you hadn't even been born yet. It came out in late 80s, 1989, I believe. And really, this was a huge improvement from the 386, and this is the 486 paper. I'll make it available on the Learn system if you want to go take a peek at it. For my 538 class, I actually have the students read this paper, and it's an interesting read, and you all should be able to understand a lot of the things that are discussed in this paper. Um, but Intel basically started the Pentium project in 1985. Okay, um, shortly after it introduced the 386, and the whole goal behind the 486 project was to execute instructions in one clock cycle. And so that doesn't mean the single cycle design that you guys did in lab, but it means having a one cycle per instruction throughput. Okay, and it's a 5-stage pipeline processor um, that actually implements the Intel architecture. The other major goal that they had for the 486 project was 386 compatibility, and this has been Intel's goal for every single processor that they've designed. That has to have backwards compatibility, and the reason is like right here they show in table 1. They show all the amount of software that's already been developed for this given processor, and so they don't they want you to be able to run all of your old software just with new hardware and run it faster. A couple things I want to point out. This particular publication was published in 1990 in Micro, I believe. Micro is a well-known computer architecture conference that still very well regarded today. Okay. Here's a little diagram of what the 486 has, and one of the big changes to the 486 is the floating point unit is now on chip. Okay. Previously, the floating point unit for the 386 was referred to as the 387. The 387 was your math coprocessor. So the 386 did not have a floating point unit on chip. Okay. The other thing that the 386 did not have on chip is cache. Okay. And the 486 does. So the 486 now has an on-chip cache. Okay. And we're going to talk. This will be a nice little segue into chapter 5 because we're going to talk a lot more about caching. And what I'd like to do is after we've talked about caching, I want to go ahead and return to this paper and talk about a few more details in this paper that you don't quite know enough for us to discuss today. Okay. Okay. So there's a lot. The first uh, couple pages is all on the caching system, and so we'll come back to that. Just from a high level, though, it's a unified cache, which means that cache stores both instructions and data. Okay, and the way they accomplish that is they have an instruction buffer that allows them to read the the cache when the processor is not performing a data reference, and that buffer holds 3 or 4 instructions worth of data. Okay, 16 bytes I think is what it was. Okay, so again, there's a lot of information here on caching, and really we need to discuss these terms before you all can appreciate them. So, but here's something you can appreciate right here. Okay, this is a pipeline execution diagram. Looks pretty familiar, right? And here's another one, right? So we've seen these. Okay, and so um, what Intel is talking about here, and of course, let me see who's the author. Um, okay, Crawford. We'll refer to Crawford, not Intel. Crawford wrote this. Okay. So what Crawford is talking about is the different stages in the 5-stage pipeline. So you have the fetch, you have a decode 1, a decode 2, an execute, and a write back. Okay, and In the 486 pipeline, what's interesting is not all instructions have to use the fetch. Fetch is actually pulling data from that 16 or from that unified cache into the 16 byte buffer. Okay, and so um, when you reach a boundary of the end of that buffer, then uh, a fetch will have to happen, but a fetch doesn't actually happen on every cycle. Okay, and this has to do with the complicated nature of the Intel x86 CISC architecture. Okay, where instructions are not fixed length. Okay, so basically they fetch an entire 16 byte worth of instructions, put it into a buffer, and then kind of chew on that buffer. And then once they're done, then they pull another one. And then of course, when you have a jump that changes control flow, then a refresh has to happen. Okay. And then the next stage is the decode one, and decode the first decode stage is essentially looking at the very first byte of the instruction to determine um, what kind of instruction it is, and then also where is the next instruction boundary. And that's what's challenging about x86 is it's unlike a RISC ISA where it's a fixed 32-bit boundaries. Um, the pipeline doesn't actually know where the next boundary is until it's actually partially decoded the instruction. Okay, so it has to know where the next boundary is, so then on the next cycle it can then begin the D1 stage on that next boundary. Okay, and so basically it determines enough information that it needs to know for the next stage of decoding. So then, because it's a complicated ISA, then it has a second stage of decoding. Okay. Now, what's interesting is there is a small percentage of instructions that might actually have to spend 2 cycles in the D1 stage, and the paper goes into detail about those instructions. They have a particular format. The author said that it only happens like 5% of the instruction execution, so not too bad. And of course, this paper really focuses on making the common fast, and so there's some very uncommon instructions that aren't all that fast, but the idea is that all of the commonly executed instructions they're attempting to execute with a throughput of 1 instruction per cycle. Okay. Um, and so then in the D2 stage, they then that's where it processes the either the data that's encoded into the instruction, or it starts to calculate the address of the memory location that the data needs to be pulled from. Okay. All right. Now there are a small select number of instructions that may actually take an extra cycle in the D2 stage. Okay, that's actually 5%. There, 3% was the amount of instructions that have to take an extra cycle in the D1 stage. Okay, so about 5% of the instructions have to take a second cycle in the D2 stage. And again, these details covered in the paper. I encourage you all to read this paper. Um, Okay, then we get to the execute stage, and what's interesting about the execute stage is that's where it will actually reference memory if it's if it's an instruction that needs to reference memory, and so the again in the D2 stage it has to then do the address calculation. Okay, so this is quite a bit different than the MIPS pipeline that we studied, um, and now, of course, then some instructions are doing an arithmetic operation, and that happens in the execute stage. The other thing that happens at the very beginning of the execute stage is the register read. Okay, so the register read actually takes place in the um, early part of the execute stage, and that's not too far fetched considering. If you remember that homework problem that I went over in the homework solutions lecture, uh, you saw that the register, read the decode stage and the execute stage were actually pretty lightweight. In fact, I think the way I had it, if I remember right, it was like 115 picoseconds in the execute stage and 90 picoseconds in register read stage, the decode stage for register read. And so if you combine those two, you're almost at you're at like 205 picoseconds, which was very um, it was which if you remember the fetch and memory stage, I had at 200 picoseconds. So we could actually combine the register read and the ALU execution. Okay, and this paper also talks about the forwarding paths. It needs less forwarding paths. It really just needs a forwarding path from the write back into the execute stage. So that's kind of nice about this 5-stage pipeline compared to the MIPS one that we talked about. Now, the author Crawford talks in detail about why they chose to architect the 486 in this particular manner. And it was mostly to get rid of that load delay. And so if you remember in a RISC processor, when we have an instruction that immediately follows a load word in program order, and it's consuming a register that the load word is producing, then we have to have a cycle of delay there. So one of the big things that the RISC guys always talk about is, well, we can get the compiler to insert a valid instruction there. And in your homework, I had you rearrange code to eliminate no-ups. Of course, I screwed up and gave you code that didn't need any no-ups, but I'll probably correct that error on the exam. But anyway, the point is that that the RISC folks have the compiler to come in and save the day and rearrange things to eliminate that load word. But one of the things that Crawford points out, which is a very good point, and one of the challenges Intel's always had when designing their pipelines is that they're targeting shrink-wrapped software. Okay, so this whole section, you can read this whole section here. It talks about exactly why they're trying to eliminate the load delay in the RISC machine. Okay, so that delay that immediately follows the load word, and so if you think about it, folks that would be buying a 486 would be folks that were using a 480 or a 386 in the past, and they have all this software that they've purchased. Well, they don't want to have to repurchase software. They want to just buy a higher performance machine and run all of their software on that new machine. Okay, and so including the operating system. So Intel and Microsoft have always worked hand in hand, and of course at this time there were also Unix systems that were running on the 386, but a lot of that code was readily available and you could actually recompile. But in the case of if you're running Windows, it's not readily available. The source code's not available. You can't just recompile. Okay, so for Intel, backwards compatibility has always been really important. So what they were saying is if they didn't architect out this load delay in their pipeline, then they would suffer poor performance. Okay, they would not be able to achieve that throughput of one clock cycle per instruction. Okay. Now there are situations where it will have to stall, and that's what they talk about. Okay, right here. And so if you have a producer-consumer relationship where the value you're getting from memory, and x86 instructions are quite a bit different than the RISC instruction. This particular move is actually pulling data from memory and putting it into this register. So it's like a load word. This is a load word. Okay, and then this add here, this add is an instruction that actually reads, takes this register value and calculates an address, grabs that value from memory, and then adds it to this other register, well, which happens to be the same register. Okay, so a whole lot of fun going on here. This is welcome to CISC. Okay. I love this 486 paper because the 486 was a marvel compared to how easy it is to pipeline with a RISC machine, which is why we start out by showing you the RISC pipeline. But I like to show you the painful CISC pipelines to well round your education. Okay, so anyway, so this particular this ad goes and reads a value from memory using reg1 as the address to that location, and then adding the value that's in there to reg1. And so what they're saying is that in this particular situation, the D2 stage is when we actually calculate the address, and so as we see here, the pipeline had to insert a no op or a bubble, very similar to the diagrams you all are drawing at home, okay, and stretch out the D2 stage so that you could forward. And I'm trying to remember if they had a no, they didn't. They didn't. They didn't have a diagram that shows. But basically, then the forwarding would happen from here to here. Okay. Okay. So they call that the pointer load delay. Okay. Anyway, so it has some situations where it will have to add no ops in the pipeline. Okay. All right. The other thing that's a little tricky with the x86 is their jumps take 3 cycles. Okay, so they're handling the jumps, okay, in the execute stage, which is 1 cycle later. Okay, that's 1 cycle later than where the RISC pipeline handles it. Well, the RISC pipeline handles it in the execute stage, but remember, for this x86 pipeline, the 46 pipeline, the execute stage is actually 1 cycle later. Okay. Um, so here in Figure 6, they're showing uh, that because of this jump, it has to then orchestrate a new fetch. So it'll fetch another group of 16 bytes and begin processing them. So if we look at Table 3, we see, I like Table 3 because it compares the 486 here to the 386 and to 2 RISC machines. Okay, this is Sun SPARC architecture, which is very similar to MIPS, and then this is Motorola's 88100. This was a replacement for their 68,000 ISA. The 68,000 ISA was a CISC ISA, and this was Motorola's replacement of that with a RISC ISA. Okay. And so what this table shows us is this is the clock cycles counts for instructions. So they're very similar to kind of like problem 1 that you all did in the homework. Okay, so and so these are average cycle counts for these given instructions. Okay. And we can see for the SPARC architecture, a load has a delay of 2 cycles, and that's probably because of the load delay. Interestingly enough, of course, the compiler can rearrange the instructions to probably bring that down to 1. I don't know. The store instruction is 3. That's kind of interesting because most of the time with stores, you can usually throw them off into a store buffer and then keep processing instructions. So I don't know why the store for the SPARC architecture has 3 cycles. Okay, ALU is 1, and that's because you can do data forwarding and all of that. We saw that in our pipeline. Jumps are 1, probably because I believe the SPARC architecture supports a branch delay. Okay, so with the branch delay, as you saw, you can execute a jump in 1 cycle. Okay. By the way, the x86 has no concept of a branch delay. Wasn't built into the ISA, so that's one of the reasons they suffer so badly on um, jump instructions. They call their branches jumps or conditional jumps. So just a little bit of a terminology difference. They just call them all control flow instructions jumps pretty much. Except they do have this special call instruction. Whoops, I didn't mean to cross it out there. It's like, well, that's what the risk guys did. The risk guys use a special version of a jump instruction. The x86 has a specific call instruction, and that's because it does some stack manipulation and stuff. So that's requiring 3 cycles to do a call, and a jump, whether it be taken or not taken, still requires 3 cycles. And actually, I'm not exactly sure why a taken jump or a not taken jump would require 3 cycles. I just don't know enough about the x86 ISA. That's one of my goals this summer is to study the x86 architecture, the instruction set architecture, because I've studied the machines quite a bit. That's what's interesting. I've studied the actual microarchitecture of the 486 of the x86 series quite a bit. I've studied the 386, the 486, the Pentium Pro, and the Pentium 4. Which was the NetBurst architecture, and then the i7. So I've studied those microarchitectures, but I actually haven't really sat down and studied the instruction set architecture itself, right? You're probably wondering, well, how the hell can you study the microarchitecture with not knowing the instruction set architecture? I have a vague idea of what it looks like. Okay. All right, continuing on. So again, one of the main premise of this computer is to compare the 486 with the RISC guys. They're saying, hey, look, and of course compare it with the 386. The thing to notice, the 386 had large cycle times for all of its instructions. It was kind of like a half-assed pipeline. It was like a 3-stage pipeline, but it just it just wasn't obviously a very good pipeline, a very efficient pipeline at all. It was hardly even pipeline, to be honest with you. I think it's a bit of a stretch to call the 386 a pipeline architecture, but somebody may disagree with me on that. Anyway, so again, they're saying, hey, look, we can actually perform with the RISC guys, and we can outperform the 386. So what we see is this is executing Drystone benchmarks, which Drystone is not a very good benchmark suite. If you take a class on benchmarking, you'll study Drystone and understand why it's like a toy uh, benchmark. It doesn't accurately represent real application code, but a lot of folks used Drystone at the time. Keep in mind this paper was published in 1990, and so Spec just had recently come out with Spec 89. Okay, so but in terms of Drystone, we can see that the 486 sits between the Spark architecture uh, and the MIPS R3000. Okay, which the R3000 isn't listed here in Table 3. That's unfortunate. Um, well, so the R3000 is a 5-stage pipeline. Okay, so if you look at the R3000 manual, the pipeline looks pretty much identical to what we study in the Hennessy and Patterson book. Oh, real quickly before I forget, I don't want to forget to point this out. This is kind of cool. When I read a paper, I kind of look at the references and whatnot, which is a good thing. You should get in the habit of doing that. But look right here. There is your co-author of a textbook cited in this paper. Okay. All right. Because they were they developed the MIPS processors, and then that's Hennessy. Okay, Hennessy is the MIPS guy. Patterson was the RISC guy from Berkeley. RISC 1. Okay. All right. So we can see that the 486 is doing quite well compared to the RISC guys. And look, lo and behold, we have spec benchmarks. Okay, so this paper was a very well written paper. And so I think they messed up here. This legend process of elimination tells me that this graph, upper graph here, is the R3000. Um, oh, real quickly, I forgot to mention here in this table, uh, more is better. Okay, so in this particular graph, the R3000 is outperforming the 486. Okay. And in this graph running spec benchmarks, we also see that the R3000 is outperforming the 486. The 486 in the spec benchmarks is actually, I would say it's slightly outperforming the um, Spark processor. Okay. I don't know the details of this particular Spark processor. If I had to guess, I would guess it would be a 5-stage pipeline. I'll have to do a little digging. Interestingly enough, by the way, they all run at 25 megahertz. So it's not like we have a clock rate difference. They're all running 25 megahertz, and the authors talk about their evaluation methodologies and also where they got the data for these machines. Okay. So it's a very good paper. I encourage you to read it. You should be able to understand most of it. Um, the cache stuff will be a little foreign to you. But anyway, okay. All right. Let's go back to, I was going to talk about the R4000, but really, to appreciate the R4000 architecture, we got to cover a lot of cache stuff because most of the extra pipelining that's done in the R4000 is to speed up the caching. Which, if you remember in your homework example that I gave you, I basically showed that the fetch and uh, the fetch and the memory stage are the critical path of the processor, and that is pretty typical. And so that's what the R4000 does, is it basically splits those stages and so into two. Okay, and so you split the fetch stage into two, you split the memory stage into two, and then because of caching things that we're going to talk about in chapter 5, we have to have a third stage. So the memory stage actually takes 3 stages. So in the R4000, the fetch stage takes 2 stages. Okay, so that bumps us from 5 to 6 stages, and then the memory stage takes 3 stages rather than 1 stage, so that bumps us up to 8 stages. Okay, I will show you the MIPS R4000 paper after we cover caching. Okay, all right. So let's go to the remainder of Chapter 4. Let's go ahead and finish off Chapter 4. And at this point, you kind of have a vague idea of what the 486 pipeline looks like and how it differs from the MIPS pipeline that we talked about. And of course, you see that in terms of performance, it's fairly comparable. The R3000, which was the 5-stage pipeline MIPS processor, outperforms the 486. But the thing is there were a lot of compiler optimizations that the that the MIPS processor is able to take advantage of. Okay. The other thing the MIPS processor has is it has a split cache, which, remember, I talk about having separate memory ports for fetch and memory access. Well, and that's a structural hazard, right? So the R3000 5-stage pipeline handles that by having a split cache. We'll talk about that when we get into Chapter 5. The 486, as you remember, I mentioned, has a unified cache, so then it uses this instruction buffer to resolve that structural hazard. Okay, so to relate back to hazards that we talked about, there's a hazard involved with the cache and the fact that you have to fetch instructions at the same time as access memory. So a workaround for that is to have a separate instruction buffer. Okay, and a number of RISC processors have also done that similar technique, which is have a unified cache, but then have an instruction buffer um, for um, for resolving that structural hazard. And I'm trying to think that there's a common risk architecture that I looked at recently that did that. Okay, um, so all right, so let's talk about uh, more aggressive levels of instruction level parallelism real quickly. So far, pipelining, we've talked about pipelining till at least I'm blue in the face, and that's one the the most fundamental instruction level parallelism technique. But if we want to more aggressively exploit instruction level parallelism, we can do super pipelining, which is what the R4000 was doing. We can do superscalar, which superscalar basically means fetching multiple instructions per cycle. So that was a competing technique with super pipelining at the time. In fact, if you go and look at the R4000 paper, which you know what? Let's just go take a look at it. They specifically, the reason I want to take a look at it is because they specifically mention that the various methods of improving instruction level parallelism is through either super pipelining or super scalar. Those were the two competing techniques at the time. The R4000 paper came out in 1992. Okay. We won't look at this paper in depth yet till we get to till we cover more of chapter 5 stuff, because it's pretty complicated. It makes the 486 paper look like a real easy read. Um, but let me see here. Let me pause the video so I can find what I'm looking for, and then double check that this thing is actually recording. All right, back again. So what I did is I went through and I looked and highlighted the different things that I was interested in talking about, and on the R4000 paper, since I decided, yeah, I might as well go ahead and talk about it. First thing is, of course, it's a 64-bit architecture. The R3000 was a 32-bit architecture. Okay, so this is in 1992. That's quite a bit ahead of its time. Um, and like the 486 paper was spending a lot of time talking about improving upon the 386 architecture, the R4000 paper is talking about improving upon the R3000 paper. Okay. Um, I mentioned this term super pipelining, and we can see that the R4000 specifically references super pipelining right here. It says, although the super pipelining increases the cycles per instruction due to longer branch and load delays, it greatly improves the achievable cycle time. So, as I have mentioned in the past, is that one of the downsides to going with deeper pipelines is you have more data hazards and control hazards, and that's essentially what they're talking about here. And so so you have longer branches and load delays to deal with. Okay, and then the second part I have circled here, they're talking about super pipelining versus super scalar. Okay, and they're basically saying, yeah, that these are two ways of achieving or increasing instruction level parallelism. See, there's that term we're actually going over just right now. And so there's those two kind of competing methods, but they looked at super pipelining as a simpler alternative. Okay, and they say that right next to this extremely complicated diagram in Figure 4, showing how this sucker works. So. Um, you know, once we cover chapter 5, you probably have enough knowledge to go through and read this paper and understand it. This paper is heavily uh, cache based. Okay, so there's a lot of discussion on caching, because what they were basically doing was pipelining the caching system. Okay, so here are the different pipeline stages, and so um, you have this instruction fetch and instruction second, I think is what the S stands for, and then a register file stage. Then you have the execute, and then they call this the data first stage. Yeah, the data first stage, that may be the instruction first, instruction second, register file, execute, data first, data second. Um, TC is tag compare, and then write back. Okay? So really, if you think about it, these two stages, that's your fetch stage. Okay, this is your decode. This is your execute. Notice execute is still one cycle, and they even talk about that. Now, there are certain instructions, 64-bit instructions specifically, that have to take 2 cycles in the X stage, just like the 486. I keep saying the Pentium, but the 486, they have to insert those extra cycles in there. And then really, these 3 stages right here are the what used to be the MEM stage on the 5-stage pipeline, and then write back's the same. Okay. All right. Just wanted to show you. Look, more pipeline diagrams, right? So it gets even more fun with the with 8 stages. But see, all of this looks familiar. You guys are doing this in your homework. So when I ask you for a pipeline diagram, this is what I'm looking for, right? All right. And then this pipeline diagram even shows where all the forwarding is happening. Okay. And here we talk about the branch delay slot. Okay. And all of this stuff, this was 1992. I believe this was also a micro paper. Let's see. Yep, IEEE micro. Boom. All right. Okay. This is talking about the arithmetic logic in the processor. This is a very well written paper, by the way. I definitely have my grad students read this paper. And look, we're talking about slips and stalls and all of that fun stuff. And exception handling. See? So all the stuff that we're talking about. So slips, stalls, and exceptions. Okay? And it goes into quite a bit of detail about each of these. And then most of this stuff that follows is all about the memory hierarchy. Okay, well, in fact, here, look, it even shows memory hierarchy. Okay, so once we cover chapter 5, I'm going to come back to this paper and we'll talk more about it. And then it even talks about the implementation. So this was implemented in a 0.8 micron, which if you remember, well, I don't know if you remember. Well, the latest we're kind of around 22 to 12 nanometer. Okay, so this is 800 nanometer. Okay, um, okay. Let's see here. This is actually talking about cache coherency, which is an advanced topic of chapter 5 that hopefully we'll get to. Cache coherency is what allows processors to share memory. Okay, and this processor was designed from the get-go for a multiprocessor environment. This was in 1992. Okay, and so what was interesting is the MIPS processors were being targeted for high-performance computing, whereas the Intel processors at the time, their main market was the PC market, and they were trying to get into the mini computer market. Okay, but MIPS was high performance, so multi-core in 1992. Okay, the only other thing I wanted to cover was, just looking real quickly at the performance. And so now in this case, this particular clock rate is at 50 megahertz, which is twice that of the R3000. Now, it would be unfair to compare the R3000 and the R4000 with the clock rate fixed, because remember, the R4000 is doing super pipelining, and the whole point to super pipelining is to increase the clock rate. And so, and even the paper points out that the CPI of this design is going to be less than that of the R3000. And in fact, they even show what the CPI is using spec benchmarks. Okay, so they simulate the spec benchmarks, and they can calculate the CPI. The best CPI they get is 1.5, and that's with a 4 megabyte second level cache. We're going to talk about second level cache here in chapter 5. Okay. Anyway, with a 4 megabyte second level cache, it can achieve a CPI of 1.5 cycles per instruction. And so if we look at that, the simulated spec ratio is 63. And remember, higher is better. So let's go back and look at the 486 because it actually shows us the spec ratio for the R3000. And we see that it's about 20. Okay, so that's a significant difference. Okay, now you might look and say, "Wow, that is a much higher than I would have thought." But we can see. Let's just look at one particular benchmark, like GCC. GCC is always a good one. GCC is not all that cache friendly, and it's not all that branch predictor friendly, as we talked about last time. Let's go back over here. And we look at GCC's about 20. So there we're only seeing about a 2.3x improvement in performance, okay, on GCC. And let's just pick another one. Let's pick this. This one's not so good. So we're looking at about 17. Okay, and that's Ignat, which is right. Oh, it might not be here. Oh, no, here it is. Wait, is that the same one? Yeah, that's the same one. Okay, so 54. So that's quite a definitely more than a 2x improvement in performance. Okay, but then look at this Matrix 300. I mean, this thing's just off the wall, and I don't think they show the Matrix 300 on this one. No, but they show the Espresso, which is 17. Sorry, I could do this all day. So that's 54, which is in line with this one. So yeah, we're seeing anywhere from like a 2 to 3x speed up on the R4000 compared to the R3000. And then keep in mind that the R3000 was faster than the 486. Okay, and the 486 came out in 89. This came out in 92. So you can imagine how much faster the R4000 was compared to the 486. And it was, because, well, the R4000 was pipelined, super pipelined, and 64-bit. Okay, which explains that explains why some of these floating point operations are much faster. Okay. All right, let's go back to our chapter 5 material. Let me see how I'm doing on time here. I get carried away. I think I've still got some time. All right, so super pipelining, super scalar, and then out of order execution. Okay, out of order execution is a fun one, and we spent a lot of time talking about out of order execution in 538. Okay, so just to recap, super scalar is actually fetching multiple instructions per cycle. Hey, look, I have a slide on the R4000 right here. Well, we already pretty much talked about that, so we can move on. But I do want to point out that modern architectures are 14 stages or deeper. So what was considered super pipelining back in 92 is just, oh, that's just pipelining now. Okay? Alright, superscalar refers to fetching, executing, committing multiple instructions per cycle. It's not just enough to fetch them. You have to actually, the width of the pipeline, I look at it as increasing the width of the pipeline, needs to remain the same throughout the pipeline. Actually, honestly, what happens is you actually fetch more instructions than you commit. So it turns out with superscalar design, your front end of your pipeline is a little bit wider than your back end. We would talk about that in 538. Okay. So super scalar allows us to achieve better than a single cycle um, per instruction. Okay. Here I mention an example is the Pentium. Okay, and I've got a paper to show you on that one. Okay, um, and so let's go take a look at that. Here it is, the design of the Pentium. Okay, so here, of course, this paper talks about its predecessor, the 486, which we just finished talking about. It's implemented in a zero point 0.8 micron process technology, which is what the R4000 was implemented in. Okay, and so this paper came out in '93. So this paper came out a year after the R4000 paper came out. Okay, but anyway, here we see the super pipeline is basically two 486 pipelines smashed together. Okay, they share the first decode, so the first decode happens, and they're joined. They in the first decode you're actually decoding multiple two instructions at once. But then at that stage, it can then split them off into the second decode. Okay, so the first decode is used to look for data dependencies between the two instructions and any instructions that are in ahead of it in the pipeline. Okay, superscalar. I would agree with the authors of the R4000 that that super pipelining is a simpler technique than superscalar. The super pipelining is going to require a number more forwarding paths. Okay, but superscalar requires a lot more data dependency checking. Okay, there's certain things you have to check before you can let instructions flow down separate pipelines. Okay, but these are two separate pipelines, and so then you have this is the 46 pipeline. So you have the ALU or cache access. Remember, those are both done in the execute, and then you have the write back. Okay. Um, yeah, this diagram's hard to read. We don't really have to go over that. Interestingly enough, which again, once we talk about Chapter 5 cache um, stuff, they chose to go with a split cache. Okay, um, so one of the things they mention here is that the 46 used a unified cache, and one of the ways they achieve performance is actually going to a split cache. Okay, so separate cache for the instructions and data. Okay, right here they talk about it. So again, the Pentium, that's how they chose to achieve better performance than the 486 and the R3000 was to go superscalar. Okay. Now Spec 92 came out, and so here they're simply comparing to the 486. They're clocking at 66 megahertz. Okay. So they're actually achieving a slightly higher clock rate than the R4000. Okay, even with the same process technology. Okay, and a shallower pipeline. So I'm not exactly sure how they're doing that, but we can see that it's achieving substantial speed up. Um, so here they're showing this is your spec ratio. Okay, now this is spec 92, not spec 89, which is what the other one used. But let's just for a moment here, just bear with me. So we're going to look, and it's about 20. Okay, a little bit less than 20. And oh, by the way, this is a 46 running at 33 megahertz, and then this is a 46 running at 66 megahertz. Okay, so this is going to this one's achieving a spec ratio with spec 92 of 20. Let's go back and look here. And so yeah, that makes sense because this is running at 25 megahertz right here, and it's about 13. So yeah, you bump it up to 33 megahertz, you're going to be around 20. Okay, and And so then now we see that the Pentium is actually running at 60. Okay, so it's 3 times the speed of the 46. So what that means is that it's going to be comparable to the R4000. Okay, if I had to extrapolate from this information. And again, this paper goes into the memory hierarchy and all that. These are very well written papers, and that's why I have my graduate students read it. All right, let's go back to the lecture slides. Okay, so we're almost done here. Let me just finish this out. So all right, so super scalar, super pipelining, and then what came after that was out of order execution. Okay, and so what we found by super pipelining and super scalar is that we're limited in performance by our instruction order. And so if we could dynamically reorder instructions, okay, we could then achieve even more performance. Okay. And so, so the thing to note is both the R4000 and the Pentium were in order pipelines. Okay, and then architectures that followed that were out of order. For MIPS, they had the R10000, and that was an out of order super scalar machine, super pipelined, all of that. Super scalar, super pipeline, and out of order. And then for Intel, it's they started going into the Pentium Pro and all that, which was the 586, the 686, and so on and so forth. Okay, so this is just from a high level how we do out of order execution. So first of all, we have in order fetch and decode. Now again, this actually looks kind of similar to the Pentium diagram where we had 2 different pipelines. Okay, but the Pentium was much more rigid than this. This is a very flexible architecture. So we fetch and decode instructions in order, and then we dispatch to these reservation stations. Dispatch to the appropriate reservation station depending on the given functional unit. So we have FUs all over here. FU here, we got an FU there, an FU all over, right? Okay. So, and we can have different varieties of functional units. So notice we're calling them functional units instead of ALUs. So an integer functional unit actually does what our integer ALU does in our integer pipeline that we've talked about. And then rather than having a floating point unit, we actually have just a floating point functional unit. Okay, and then we have a dedicated functional unit for loads and stores. And you can have a variety of different functional units. Sometimes you'll have a separate functional unit for handling branches, or sometimes the integer unit will handle it. The other thing I want to point out is, look, we actually have 2 integer units, and then they dot dot dot. So we can have multiple ALUs now in this design. So once you pay the huge penalty for going out of order, you can then very easily increase the amount of instruction level parallelism by increasing the functional units. Okay, and again, this is the focus of my 538 class. We talk a lot about this. The reservation stations just simply buffer up instructions that are ready to go. So everything is in order at the front end of the pipeline here. So it's in order here. Oh, I don't have to write it. It's written right here. Okay. Looks a lot better than mine. And then when you cross this line, it becomes out of order. Okay. Now, what's interesting is for the purposes of precise exceptions, we just talked about that, remember? Okay. We now enforce an in-order commit. Okay. So we fetch instructions and decode them in order. We allow them to run out of order, and then we somehow magically put them back into program order before allowing them to commit state. And we do so with what's called a reorder buffer, which makes sense. It reorders. It puts them back into original program order. Okay, so the reorder buffer is this magical mechanism that keeps track of program order even when the instructions are running out of order. Okay, so it's a whole bunch of extra state that's required to do this, but it's definitely worthwhile. If this fascinates you, take my 538 class. All right. Okay, let's just look at a couple of charts, and then I swear we'll be done. And I got to go to bed. So here we start. Look at that. The 46 in 1989 and the Pentium in 1993. Pentium Pro in 97. Okay. Let's look at the number of pipeline stages. Yeah, we just looked. The 46 is 5. The Pentium is 5. And the issue width 1, 2. We just talked about that. Cool, huh? No out of order execution. I mentioned that. Those are in order pipelines. Look at their thermal design power. 5 watts for the 46 and 10 watts for the Pentium. Those things are tiny. Okay. All right. Let's go to the Pentium Pro. Pentium Pro was in 97. So that's around the same time as the R10000. Okay. We went to 10 pipeline stages. We're now issuing 3 instructions per cycle, and we're running out of order. And we took a jump on our power. Okay, and it just keeps getting worse. Intel got addicted to speed here, and we see here the uh, uh, the Pentium 4 was where they hit rock bottom, so to speak, on that speed, and 31 pipeline stages, issuing 3 instructions per cycle, out of order execution, and a 103 watt thermal design power. Just to give you a comparison, I bought a server recently that has it has 20 cores on it, and its thermal design power is 86 watts. So we have gradually reduced the amount of wattage. And of course, well, they give you an example here. Um, See, that's the other thing. Nowadays there needs to be a column here that actually indicates how many cores they have, right? Okay, so the Intel Core started with 2, and then they moved up from there. And now 12, 20 cores is not unusual. But one thing to notice is they went down on the number of pipeline stages. So that's when we started going to multi-core. So right after the Pentium 4, they hit the maximum thermal design power, and decided we got to do something differently. So they stopped going with such an aggressive pipeline. They backed off with a shallower pipeline, more reasonable sized pipeline, I might say. They did increase the superscalar, so they went to 4. And then, oh wait, they do have this column. Look at that. Jesus, apparently I didn't even look at this darn chart. Okay, here's our core count. Yeah, and our core count, we started with 2, um, 1 for that one, and then now we have 8 here. So, and notice the clock rate dipped down. Okay, it got really high here at the Pentium at 3.6 gigahertz, and then it started going down, and now it's kind of settled. A lot of processors will run at in the 3 gigahertz range in turbo mode, but our thermal design power is much lower now. Okay, so that's kind of a computing trend. All right, this chart, and it's the last one for the evening, shows the ARM A8, which is ARM's application processor. Okay, so it's a low-end mobile processor with the high-end i7. These two, I would say, are on opposite ends of the spectrum of application processors. The A9 is not necessarily an embedded processor. It's what you would find in a low-performance mobile device, and so they're in opposite ends of the spectrum when it comes to application processors. So thermal design power is 2 watts for the A8, and it's 130 for the i7. Okay, the A8 only has 1 core. Now this material is dated. Most of this book was updated in 2014, so most of the material is from the 2012 to 2014 time period. It's very common to have mobile processors with multiple cores now. They have 4 to 8 cores. In fact, we're even looking at going multi-core on ours as well. The A8 does not have floating point. The A9, which is the successor to the A8, does have floating point. It is multiple issue. It's 2 instructions per cycle, okay, and 14 pipeline stages, but it's in order. And there's its cache system. That really doesn't mean a lot to you right now. 32 kilobytes of instruction, 32 kilobytes of data cache. Remember, we have to keep those memories small because they run at the speed of the processor. And then the next level cache is 128 kilobytes to 1 megabyte. The second level cache depends on the SoC, the system on a chip that the A9 is built into. Whereas the Intel Core i7 is not a system on a chip. It's a single microprocessor, and so the cache is fixed. And it's at 256 kilobytes, and we'll talk more about this when we talk about memory hierarchy. But it actually has a third level of cache. Oh, here's our branch predictor. 2-level, we know what that means. That's a correlated predictor. Same thing for the i7. This is dated. The i7 is doing all kinds of crazy machine learning techniques now for branch prediction. The i7 is out of order, and it's 14 stages, and it can issue 4 instructions per cycle, and has 4 cores. All right, with that, I hope you've enjoyed the lecture. I apologize, I'm almost positive I've gone over, but anyway, hopefully it was good material for you.